Now we're going to look at graphs that have asymptotes. So asymptotes. I've just drawn a random graph here to try and illustrate the different types of asymptotes. I have no idea what the function would be, but anyway, so possibly it doesn't even exist. So asymptotes are basically a way of describing what happens out at the extremities of the function. So infinity and so on. So we could have a vertical asymptote. Now a vertical asymptote happens when there's an exclusion in the domain. So it'll happen if the limit as x is approaching whatever that a value is going to infinity or negative infinity. So on the one I've drawn, it's actually going to both. On the left-hand side, it's going to positive infinity. On the right-hand side, it's going to negative infinity. So that's one type of asymptote. With the vertical asymptotes, functions do not touch or cut them because they are exclusions in the domain. So there's no way the curve will cut or touch the vertical asymptote. Right, we could have a horizontal one. Let's draw one in there. Again, it's telling us what happens at the extremity. But now we're talking about out at the extremities of x rather than the extremities of y. So a horizontal asymptote tells us what happens as x approaches plus or minus infinity. So the vertical one was when the function is approaching plus or minus infinity. The horizontal one is when the actual x value is. And for that reason, it is possible for a function to cut a horizontal asymptote, and as I've got it doing here, because when it's not near infinity, it's like that asymptote doesn't exist. And when we talk about not near infinity, when you think about it, every number is not near infinity, because infinity is so far away. Even infinity minus 1 is not near infinity, if there was possible to have such a number, which of course it's not. So those ones, as it goes out to the extremity, we've only got one on the right-hand side for this one. The curve will bend towards the asymptote. The curves always bend towards the asymptote. The third type is an oblique asymptote. An oblique just means at an angle. So this one is when x approaches plus or minus infinity, so does the function. So the first one, the function approaches plus or minus infinity, so that's vertical. Horizontal, the x values approach plus or minus infinity, and then the oblique ones, they both approach plus or minus infinity. And so in this one, we've got that on the left-hand side. We can see the curve is approaching that asymptote. Now, an oblique asymptote is technically a straight line. It is possible to have curves for asymptotes. It all depends how that curve is approaching infinity. So an oblique one, it's approaching it like a straight line, but you could have ones that approach it like parabolas and things like that. We probably don't see a lot of those, but it is possible. As I say, it is possible for a function to cut or touch those horizontal or oblique ones. Okay, probably the most common one that we see is our hyperbola, or more in particular what we've seen so far is technically called not just a hyperbola, but a rectangular hyperbola. And y equals 1 on x is the most basic one of that. That's a graph that demonstrates inverse variation. So as one of the values gets bigger, the other one gets smaller. So as x gets bigger, y gets smaller. As y gets bigger, x gets smaller. So it's inverse relationship. Rectangular hyperbola, why is it called that? Well, that's because the asymptotes are at right angles to each other. And just like the vertex in a rectangle is a right angle. So that's why we call it a rectangular hyperbola. And once again, every rectangular hyperbola could be created from the basic one of 1 on x via different transformations. So a translation, a rotation, a reflection, or what have you. How would you recognize it? We look at the function. I wonder what that is. Well, one of the variables will be the numerator in a fraction. Well, y by itself is like y over 1, so it's in the numerator. And the other variable is in the denominator. Of course, another way we could see it is like the alternative way I've got written there. We see the two variables multiply together. Well, perhaps that's going to be some type of hyperbolic function. Another common function that has an asymptote is our exponential function. Now, what I've said there is the orientation of it is determined by the base. An exponential will start out small and then increasingly rise. But that's if the base is bigger than 1. So if the base is bigger than 1, it would have that sort of shape. Starts out nice and shallow and then increases more rapidly as the function goes along. If the base was less than 1, and when I say less than 1, I mean between 0 and 1. The base is always positive. It's meaningless to have an exponential with a negative base. If you do one with a negative base, do you know what you get? You get a series of just random points. Because if you think about it, you're saying a negative number to the power of something. Well, as soon as I go to the power of a half, it doesn't exist. Power of a third, it does exist. Power of a quarter, it doesn't exist. Power of an eighth, yeah, no, that wouldn't exist either. You get what I mean? So the odd ones are going to exist. So you basically get random points. It's weird. Okay, so what happens with the ones in between 0 and 1? It flips the other way around, starts out steep and comes in shallow. How do you recognise it? Well, this one's a little bit of an easier one to pick. Oh, look, it's in the power. Hence the name exponential, because another name for power is exponent. That's where it gets its name from. As I say, base has to be positive. Okay, there's the first bit for today.